heating and doing stuff, if that matters.
Okay, reaction solvent, what page? 20L?
Sure.
Reaction solvent for lab this week. Question, you have three choices. What is MECN, abbreviation for? Acetonitrile? Yeah, acetonitrile, acetone, or ethanol. Which one would you think is best to use, or which one you're going to choose to use? Ethanol is a protic solvent. What does protic solvent mean? It has a proton that can participate in hydrogen bonding. Okay? That's what a protic solvent is. Acetone and acetonitrile do not. Yes? And why don't you like the protic solvent, or what's your question about the protic solvent?
I'm just wondering if it's going to give us like some other weird product than what we're actually looking for, because it can react well. I was wondering if it can react well with the acetaminophen once it's been deprotonated.
Deprotonate the acetaminophen, and what do you mean it can react well?
I wasn't sure. I was trying to put together all of my thoughts, and I was like, this just looks like it's going to go badly. I'm not sure exactly why.
Well, you come up with more of a suggestions of why, hypothesis of why. Anybody else consider this yet? Which solvent you're going to use? Is this reaction done at reflux?
Yes.
Okay, boiling points of solvents, is that relevant? Yeah. Protic solvent. Have you read about solvent? What's the best type of solvent for SN2? We are doing SN2, Williamson ether synthesis. Make the phenoxide, and then it attacks the ethyl group, carbon of the ethyl, kick out SN2.
It's polar aprotic, right?
How do you know that?
Because I was reading my stuff, yeah.
Okay.
So that's why I was concerned that we'd get an
Yeah,
E1
I agree with
elimination
that.
with the polar.
I agree with that. So does that help you eliminate?
It does.
Okay, yeah. All right. Need to be reading about that. We can talk more about it later or offline or something. Yeah? Okay. Elimination, right? Phosphopyridine, what does that do to an alcohol? Bam, bam, bam. Elimination protocol, yeah? Way to eliminate it out, dehydrate. Other than using acid, anybody got an answer for the first one here? One-methyl cyclohexene. And down here, yeah. That's not 2-methyl-cyclohexene, that is that the right structure?
Yeah.
That's not 2-methyl-cyclohexene.
Is it 3-methyl?
That's 3-methyl-cyclohexene. But the alkene is 1,2. One, two, three. Up here, the alkene is 1,2. But do you go 1,2 this way or 1,2 that way? Have a choice. 1, 2. The alkene is 1,2 in both cases. But up top, we do 1,2, so the methyl gets the lowest number. If we went the other way, the methyl would have been 6. Okay? Sate-F products. Why do we get the Hoffman product down here?
There's only one beta hydrogen, right, that I can react with?
The beta hydrogen down here is This is going to be the eventual leaving group, right? The eventual leaving group and the H are not trans, so they can never be trans-coplanar. Review from Organic 1. Okay. And so we're going to remove one of these H's up here, the one that is trans, right? Everybody cover this in Organic 1? Yeah? How we do on those two? Yeah? I think we did everything else on this page, yeah? Williamson ether synthesis. Anybody have a synthesis of the first compound? Which, by the way, used to be used as a fuel additive to gasoline 10, 20 years ago. Called methyl tert-butyl ether. It was added to gasoline to increase the oxygen content. So when it burns, it has more oxygen in there. Because it's a closed system, it doesn't have much oxygen around. So when it burns, it doesn't burn. Combustion is not as good as it could be. So when this is burned, it produces, oxygen becomes available in the system. Otherwise, you're just burning hydrocarbon. Hexane, octane, that's just all hydrocarbon. There's no oxygen around. But now, instead of putting that in gasoline, what they put in gasoline, what do we put in gasoline to supply some oxygen? Somebody said it. Ethanol. Yeah, it's up to 10% ethanol, right? That's to give some oxygen in the mix when it burns. Anybody have a synthesis of this compound? We make an ether, you can either make the O part. Which bond do you want to make by an Williamson ether synthesis, on the left or right? Let's take this back. Retrosynthesis, retrosynthetic analysis. I'm going to put can I put an ME on the end? It looks a little naked without it. We can have an MEO minus. Williamson ether involves what? O minus is the nucleophile and a carbon with a leaving group, right? We go back to that O minus plus, what's your favorite leaving group?
Bromine.
Bromine? Okay, we could go back to that. Or that would be breaking, that would be making which bond? Potentially, theoretically. That one there? Or we could go back, this is a retrosynthetic error, retrosynthesis. We're thinking backwards here. We could go back to making this bond by reacting methyl bromide, I'm going to say iodide, because methyl iodide is very common. Methyl bromide is a gas. Methyl iodide being a liquid is much more common in the lab. Plus what? Plus this O minus, yeah? Okay, which do you like better? Don't worry about the leaving group. You can use any leaving group you want in any of these theoretically. Which one do you like better? Why B? Because up here, this is required nucleophile to displace a leaving group from a tertiary carbon. That is no good, right? Bad. No SN2 on a tertiary carbon, right? Everybody agree? Yeah. No good. Tertiary. But this down here is going to be good. Okay. I don't like attacking an ME. Should have drawn a methyl instead. How about a CH3? Like this. That's methyl iodide, often just written right like that, correct? Very common methylating reagent. Okay. These electrons attack the carbon, kick off the leaving group, good old SN2. And if we're coming forward, we can come this way. Does everybody agree that that's going to give that product nicely? Yes, it should. There's no problems there. If you're asked to go back to neutral, that's not neutral. How would you make this? Well, the alcohol, yeah, reacted with what? Na, NaH, sodium. That would give this plus sodium plus, correct? The sodium alkoxide. And then if we keep going, we'll make this plus sodium iodide, or whatever the leading group is, sodium bromide or something. So everything can be balanced out through there. Yeah? How'd we do? How about the one below? Anybody have a synthesis for the one below? Uh-huh, good. Full Lewis structure with anything in a mechanism.
It's tricky, isn't it?
Okay, which O carbon bond we're going to make? On the right or left?
Right.
On the left, yes, not on the right. And that will go back to something like this. Yeah, we can go back to that. We can get an SN2 coming forward. Why not over here? That would be A. If we come back over, think about coming from B, it would be what? This plus what? Something like that. That's no good, right? Leading group is not on a tetrahedral carbon. Cannot do SN2 there. Now you can do a substitution reaction there, but it takes different conditions. We don't know it yet. During test 2, we'll learn about that. Very harsh conditions. Theoretically possible, but not for standard Williams ether synthesis. You don't want to go back there. You want your leaving group to be on a tetrahedral carbon, right? Okay, SN2, yes. This would be the way. How do you make the phenoxide? Phenol plus some base. What base would you use? Potassium hydroxide. Hydroxide works with phenols. You could also use carbonate or phosphate. Yes, you do not have to use sodium metal. Okay. Basically, we're not going to make the bond over here. Okay. Yeah. Everybody good with that? Down here, what's going to be formed instead in this line reaction? Not this product. Somebody have the product that's going to be formed down here? Well, KOH is a base. It's going to remove the most acidic proton. Everybody agree? What's the most acidic proton in this molecule? The carboxylic acid proton. Yes. And so the base is going to give us this here. And then when we throw in something like this, this will attack and kick that off. Yeah. And so what's now on this oxygen over here? Ethyl. Ethyl esters are often just drawn. Oh, ethyl. Oh, methyl. I can do that. Everybody good? And so instead of alkylating the phenol oxygen, we alkylated the carboxylate oxygen, and the carboxylic acid became an ester. Okay? Pretty straightforward, right? The base removes the most acidic proton. Carboxylate anions can do SN2. Again, review from Organic 1, right? Okay. Everybody good there? Cleavage of ethers. Did we do the first one already? We did? How about the second one? I don't think we did that one, did we? Somebody have products there? Can you name your products? Nomenclature of alcohols and ethers. Any questions there? Anybody name your products? Everybody agree we're going to protonate something with a strong acid? Protonate the oxygen, then what? What's the rule? If there's a tertiary site, we're going to do SN1. If not, we're going to do SN2. Is there a tertiary site? No. That's secondary, that's primary. What we're going to do? SN2? We got a Br minus. Where's it going to attack? Minus, right? Okay, attack here. Kick the oxygen off of that methyl group, and what do we get? That's the Lg that left. Plus what? Methyl bromide. You know, you can show this however you want. But the bromine is now bonded to the methyl carbon, right? What mechanism are we doing here? SN2. Could the bromide have attacked here and kicked the oxygen off there? Theoretically, it could have. Why did it attack over there?
Steric hindrance.
Steric hindrance. SN2 is largely governed by steric hindrance. It's going to attack the least substituted carbon of the two. Yeah? How are we doing with that one? Questions? Question?
Why would it not kick off at the secondary carbon?
Why did it not attack over here?
Yeah.
Well, we did SN2. SN2 is largely governed by sterics, right? Steric hindrance. Heard of this yet? So which site would it be more likely to attack? The least sterically hindered site or the more sterically hindered site? why we predicted that to be the major product attack the least. After you protonate, the Br minus has a choice. Should I attack here or here? It's coming in, it's like, sterically hindered, bam, I'm attacking over here. Right? SN2 largely governed by sterics. SN1 largely governed by carbocation stability. Tertiary, good for SN1, right? Primary, best for methyl. That's not even primary. A methyl group is more accessible than even a primary carbon. Okay, how about this one here? Product here. Name of your products? Phenol plus what? Phenol plus ethyl iodide. And protonate the oxygen, and then what? The I minus attacks where? Right here, kicks that off, and we get phenol plus ethyl iodide. Is it going to attack over here? Kick the oxygen off there? No, that's not a tetrahedral carbon. It's also more sterically hindered if you want to think about that. I mean, there are many reasons it's not going to attack over there. And so what have we done to the ether? We've cleaved off the alkyl group back to an alcohol, in this case a phenol. Okay? Could we come this way? Yeah, treat this with the base, make the minus, and then it can do an SN2, and you can kind of go back the other way. And that would be a Williamson ether synthesis. This way is called an ether cleavage, which is about the only type of reaction that ethers will do. Cleavage of cyclic ethers. Can I protonate the oxygen? What next? Cl minus. Is it going to bond over here or here? By what mechanism? Right. Cl minus attacks here and kicks these electrons off because we don't have a tertiary site available, correct? No tertiary site, so we're doing SN2. SN2 least substituted carbon. What does that give? Gives that there. The OH is just left. There's no change in stereochemistry here. It's just left that carbon. But when it leaves, it gets its lone pair back, right? Everybody good? That product can actually react again with HCl. Somebody have product after it reacts again? What chemistry can happen next? Tell me what's going to happen next. We have strong acid. Right? We can protonate. And after we protonate, how can we show this here? I'm going to kind of keep my original kind of bonding here. Give that there. Because we first what? Gonna have to redraw this. Don't we first protonate? I'm not going to do mechanism, but I will show the intermediate. Don't we protonate the oxygen? Everybody can protonate the oxygen? Then what? Then the other Cl minus comes in here and bam, kicks off the leaving group. Chlorine's going to be over here. It just pushes that methyl group that way. Chlorine's over here, the methyl group got pushed that way, still forward. That's the same thing we looked at before. It is inversion, right? Everybody agree? See it? Yeah? So basically, this can react twice with HCl. It can first kind of cleave the ether, but then the alcohol, we've seen alcohols can react with HX to make alkyl halides. So the chemistry can keep going. The first cleavage doesn't break the molecule in two, but it does break open the ring. Yeah? How about the second one here? Anybody have product? Anybody have product? Anybody else? Protonate the oxygen. I suggest that the product is going to be all depends on. See, if you ever use two equivalents, let's assume we're only going to use one equivalent here. Let's don't react again, because we could react again. We got an OH in the product. Could react again. You can draw your product there. It's going to be this here. Why?
Secondary carbocation.
What's our rule though? We would only do SN1 if there's a tertiary site. How strict is that though? What did I do down here? I got this plus Br minus. Where's it going to attack? Left or right? No tertiary site, attack on the left. Least substituted. But if it attacked here, the bromine would be bonded to that carbon and the OH would be on the carbon with the phenyl. I'm suggesting that it's going to, here, this is going to ionize this way and give, hopefully you got some room over there. This carbocation, then the Br minus, I should have just drawn it from there, attacks carbon here. So what type of mechanism did I do? SN1. Why? I didn't have a tertiary site available. Why did I choose to do SN1? I didn't make a tertiary carbocation. What did I make though? Secondary, but it's more than a secondary. resonance stabilized by the benzene ring. It's called a benzylic carbocation, right? And resonance makes your secondary cation as stable as what? As a tertiary. Resonance bumps it up a notch at least. So we didn't strictly follow the rule, but I suggest that this is probably going to be the outcome. So an exception to the rule could be when we have a very stabilized carbocation that could be forming. Basically, the rule tells us to only form tertiary carbocations. And if you can, do it. Well, guess what? A secondary carbocation is pretty darn easily formed as well. Yeah? Everybody knows benzene ring resonance, benzylic, yeah? Okay? Resonance stabilized. Always look out for resonance to sort of be a predominant factor to influence the reaction outcome. Everybody good? Third one down there, product, THF, some type of strong nucleophile with no acid. Product, no reaction. Ethers have to have acid to make the oxygen a good leaving group. THF is a good solvent but with strong reaction. No reaction. And that was discussed below. We already discussed it though. Okay, we're moving on to epoxides. Epoxides, this is going to be different. Okay, epoxides are unique. With epoxides, we're going to break some rules. Break some rules, largely because the epoxide is, first off, what is an epoxide? Well, the epoxide is the three-membered ring with one oxygen. It's a cyclic ether. We made these in Organic 1 from alkenes. Got to review synthesis. What reagent did we use? Like peroxy acid, the most common being MCPBA. Yes. Take this alkene, MCPBA, some type of inert solvent, dichloromethane would be a common solvent here. We can get the epoxide. I'm showing stereochemistry here because this carbon here is chiral. It's a small little three-membered ring, but that carbon is chiral, and we can get racemic outcome there. Okay. If you wanted to draw it generically, you would just, of course, just draw it like this, right? But that carbon is chiral over here. Cyclohexene, MCPBA, maybe use diethyl ether. Common abbreviation for diethyl ether, yeah. Oxygen with two ethyls. Yeah. Be done. Get the epoxide. Now that product is not chiral, right? Why is it not chiral? Plane of symmetry. Okay. Yeah. You can show the two bonds dashed if you want. It's the same exact compound. The two bonds are cis, same side, right? Yeah, you cannot make a three-membered ring trans. I mean, if this is one atom, this is two, and this is three, if these are going to be bonded together to make a three-membered ring, they have to be like this way. If the bonds were this way, how can these two hands bond to each other? You can't have a trans epoxide. Okay? And mechanistically, the alkene attacks, right? And then to leave a carbocation, if it's formed, what happens? Back bonding, and you get the, okay, you need to review mechanism. Now, some of you know what not actually formed means, but some of you have never heard that. I imagine not. So, however you were taught alkene reactions, you need to review that, okay? Of course, if we had a methyl here, and we did this maybe using THF as solvent, okay? 2 ether solvents, a halogenated kind of solvent, we get this. But that would be a chiral product, and so there we can show the 2 enantiomers. So, a new way to make epoxides. A new way. First is a review. If you take an alkene with halogen and water, what type of product are you going to get? An organic one? Halogen and water. The product is called a halohydrin. Okay. It's going to give this product here. What do we first form when that reacts with bromine? Well, mechanistically, because if there's no water here, we get a dibromide. But with bromine, the first thing is to make what type of intermediate? Bromonium ion. And then what attacks the bromonium ion? Water, right? Bromonium ion, again, you need to review your mechanisms. Bromonium ion is going to look like this. The stereochemistry here, and I'm not going to show it. But then water, right, attacks, really a choice here. Which carbon we're going to attack? This is where, back then, things were a little bit wrong. And actually, it attacks here. Takes that off. Right? That's how the OH gets bonded here, and then we lose a proton. What takes the H from the oxygen? The other Br minus that's around, okay? Basically here, racemic. You need to review mechanism for making halohydrins. But then this product, if you treat it with sodium metal or something like that, you can get the epoxide. What does sodium metal do to this? Well, the question is, what does sodium metal do to an alcohol? It essentially deprotonates it by a redox mechanism, makes the O minus. Can I just show the O minus? And sodium plus hydrogen gas. What can this do? Well, this can just go boop, to an internal SN2. That's basically Williamson ether synthesis. You make the O minus, and then, but it's the carbon with the leaving group is right there, and it goes boop. This makes the ring. So a new way to make epoxides is reacting a halohydrin like sodium metal, and you give the epoxide.
Because epoxides, like, they're so reactive and relatively unstable because of that ring tension, why does it want to do that? Is it just because that bromine is so willing to leave?
It's so willing to leave. And once we get to this point, it's going to get to this point.
Right.
That goes to this plus what? They agree that when it comes in, it kicks off the leaving group. And so one molecule went to 2. That's not really a molecule, but so it's driven by entropy.
Okay.
And it went from minus to neutral.
Okay.
And Br would rather be minus than oxygen. So there's reasons that it goes that way. Yes, it has ring strain, but it will form. And yes, epoxides tend to be reactive. And that's what we're going to be looking at. It's a cyclic ether. It's an ether. It does have ring strain. Let's look at the reactions. Because of the ring strain, reactions tend to be unique. And we can do chemistry that you can't do with other ethers. How are we doing with the video recording? You guys, for me, been able to find videos and watch? Okay, hopefully they're helpful. Reviewing. Nomenclature. How are we doing with NMR? Okay. How about on Wednesday, I'll ask you if you have any questions about NMR. Okay, reactions of epoxides. All right. It's an important topic. I'll bet you a steak dinner with I'll throw in a nice bottle of wine with it, that you'll probably see a reaction to epoxide on your final exam. Okay? Epoxide is a very common topic. All right? So let's look at it. Reactions first under acidic conditions. Mechanism. Here we go. It's an ether. When a tertiary reaction is present, go SN1. If not, go SN2. Have you heard that before?
Yeah.
Yes. All right. Something unique though. SN1 with epoxides gives inversion. Usually SN1 gives racemic, right? Why does it give inversion with epoxides? Well, let's do it. All right, here we go. Can I protonate the oxygen of the epoxide? Everybody know how to protonate an oxygen? Okay. What type of mechanism we're going to do from here? I got a secondary and a primary. I don't see a tertiary site or resonance or anything. Okay, what we're going to do here? SN2. And so the Br minus attacks where? I like it over here better. Take that oxygen off, what do we get? Br is bonded to this carbon. The oxygen just left that carbon. It's still bonded here. Everybody agree that's the product? When this opens up, there's no change in stereochemistry here. We didn't know chemistry there. It just pops open, but it's still forward. There's your product. Now this assumes just one equivalent. Because if we had a second equivalent, we could react with the alcohol again, protonate it, and then maybe a Br would come in here and we could get another Br here. Let's just assume one equivalent. Yeah? Nothing new there than we did on the other page. Nothing new. SN2. How about the one below? Can I protonate the oxygen? Now what? Do we have a tertiary site available? Yes. Bottom carbon is tertiary. So what mechanism? SN1. So what's going to be the product? I'm going to draw it twice. First, no stereochemistry. And really I need to do mechanism twice. Let's do mechanism, but what's mechanism from here? Oxygen just leaves, right? Because it's going to leave before Cl minus can attack over there. Tertiary. And that's going to give outcome here. That just opens up. But what's down here? Methyl, but charge.
Positive.
Carbocation. And what's the geometry now of that carbon? Trigonal planar. Carbocation, right? Now, if Cl minus attacked here, if we did that in organic 1, what we're for today, what would have been the stereochemical outcome? Racemic. But with epoxides, you don't get racemic. Because the leaving group has really not left. It is still nearby. Let me ask you this. Do you think these electrons are attracted to this positive charge? Yes, physics tells us yes. Minus, like, okay. So even though this sort of left, there's still some, now that looks like stereochemistry. It looks like a bond. There's still some interaction here. There's a good bit of interaction here, and I don't know how to draw it without making it look like a bond. Maybe do it smaller. There's some interaction here. There's enough interaction here that the leaving group blocks. Now this is forward. So the interaction is, now oxygen is really forward like this. There's enough interaction here. Okay, let's make this be sort of the interaction. There's enough interaction here that it blocks this forward side. And so the nucleophile comes in from the back. Let's call this an IMF, an intermolecular force. It's blocking. Okay. This is very hard to show mechanistically. What we're just going to show is an outcome. And basically the outcome here is the Cl minus is going to become bonded here. But it's going to come in from the back. And the methyl here by default has to move forward. There's your product of this reaction. It is described by me as an SN1 with inversion. It's not SN2. If this was SN2, the Cl minus would have attacked where? Top or bottom carbon? Top, because that's the least sterically hindered. So it ain't SN2. It attacks like down here, carbocap. It's a blended mechanism, really. I describe it as SN1 with inversion because SN1 tells you that you get the right carbon identified. Carbocation, it's just a carbocation is not completely free. If this thing completely ionized and went away, just completely disassociated, then it would become free, and then we could attack either side like we. Okay. Epoxides are like this. Now, actually, this is the same way in organic 1 when we made rhomonium ions. Where did we attack? See, in organic 1, we just kind of made a statement where you attacked where? Down here. Yeah? That's actually, as we have moved forward, that's actually become more and more wrong in terms of what statements we make. Because didn't we come down either another BR, okay? If it was another BR minus, if we were like brominating an alkene, wouldn't this then come in? Well, I'm going to use chlorine so I can have a different halogen. Didn't we always attack here and kick that off? But guess what? We were attacking the wrong carbon. That's not the least substituted. That's the least substituted. Remember how I described this? That, if you look back at my handout, the bromine's going to pull on one of these bonds. Which one's it going to pull more on? The bottom one? And so I showed you something like this. Partial plus, partial plus. And we attacked the most. Well, what I was really showing you is the same thing I tried to show you here today. We just didn't talk about it as much. And whenever I discussed this, we hadn't even talked about SN2 reactions. Because I covered alkene reaction before. But actually, when you do this, you can actually describe this as sort of SN1 with inversion. Because if it was SN2, the other halide should be attacking up here. Attacking this is the same as attacking this. Everybody getting it? And if you look back at that discussion from Organic 1, the handout, okay? In the end, epoxides, whenever you do SN1 with epoxides, you just get inversion because the leaving group really hasn't left enough. It's still hanging around. It still blocks that side, even though it's ionized. Okay? All right, you can move forward looking at some of these. Please be working some of these. I'm going to move ahead, okay? Have a good day, guys.